Okay, so today we begin at 32.3, talking about energy stored in a magnetic field. And this is going to be the magnetic field of the inductor, because as we know that the current is going to be curling around the inductor, the coil of the inductor, and so magnetic field is going to be inside of it. So we're going to look at the energy stored in the magnetic field of an inductor in a circuit that has a battery and a resistor. So circuits with inductors must provide more energy than those without. I mean, because when you have an inductor in there, it's going to basically be resisting the flow of your current. It's going to be creating this back EMF. It's going to be, causing the current to, the current's going to reach a maximum value, provided the resistance is very small or whatever the resistance is. It's going to reach a maximum value, but it's going to take some time, as we saw yesterday. It's going to take some time for that current to reach its asymptotic value. As t goes to infinity, it's kind of gradually it gradually reaches a value in an exponential type of way. So I was talking, we saw this yesterday. So it gradually reaches, but it's a slow process, sluggish process. And those without. So circuits with inductors must provide more energy than those without. I mean, that's just a little common sense. So energy is stored in resistors, magnetic fields of inductors, we just say L. So if we take this equation where we had this Kirchhoff loop rule here, and we had all these different voltage drops from this battery, this source of EMF, and so IR is minus IR is going to be the voltage drop across the resistor. And we also had the voltage drop across the inductor. The sum of all those voltages is equal to 0. So now if we set E equal to IR L di dt, and we multiply each of these terms by I. Why are we doing that? Because we're looking at the rate of change of energy for each of these circuit elements. What is the power produced by the battery, the resistor, and the inductor? And we also know we multiply by I because we know that one form of power is I squared R. So when we multiply it here, it's going to be I squared R. This is going to be I delta V, but in this case, it's represented by E for EMF. So same thing. So it's a power term here, I times voltage, I squared times resistance, and then L times I times di dt. And we'll do something with that soon. So I squared R, Li di dt. These are all power terms. This is the power in the battery, the power in the resistor, power in the inductor. So this power in the inductor, or energy per time in inductor, and so all these terms are time rates of change of energy. And so basically the total energy is going to be the sum of all of these small energies. So these energies of the circuit. But what we're going to do, we've already used that concept, the time rate of change of energy, to get I squared R and I delta V back in chapter 29 or 28, somewhere in there. So now we're going to get an expression for energy for this inductor, because we have a time rate of change term, and so we must deal with that appropriately. And du dt so we have that rate of change or power. So du dt, that gave us the I delta V, that gave us the I squared R, you know, by proxy. So du dt for the inductor, Li di dt, well, you can see where this is going. So we're going to get the U value for this inductor. So we have to integrate both sides here, but the dt's are here on both sides. Should be an easy integral. We are going from, you know, a small level of energy so let's say that, you know, t equals 0, nothing. Or is it just an indefinite integral? It, you know, we can have some boundary conditions, real values for both bounds. And so this is going to be L. This is going to be going from 0 to I, because at t equals 0, there is no current through the inductor, but then, you know, slowly it builds up because it takes time for that current to build up to a maximum value. We saw that in the definition of inductance, and this is going to be I di. So all I terms are in the integrand. This becomes U equals L. And when we antiderive this, remember, it's I n plus 1 over n plus 1. So that's going to be an understood 1. I to the first power is I. So this is going to be I squared over 2, or more easily put, 1/2 Li squared. So this is the expression for the energy of an inductor. This energy is stored or held in its magnetic field. Remember, the inductor is like a coil, current going around it, magnetic field going through, solenoid, and so the energy is in the red line. It's held within. So we can determine the energy density of a magnetic field in a solenoid. So we now know what a solenoid looks like now. keep referring to that. So it's like, you know, that cylindrical deal. I should have a video next time. Wire turns. There's a little base, and it's like sitting on the table. So magnetic field is going through like that, and current is going around the wires. And so the current is time varying, so it creates a magnetic field on the inside. And if we get a scenario where we have like, oh, we can put a magnet in here and we can induce a current on the outside in the wire. So there's that interchange, that marriage between electric fields and magnetic fields. If one changes, it changes the other one. It produces a change in the other one, and so vice versa. Time varying current or electric field produces a changing magnetic field. It's all symbiotic. Yep. Like the black background. Okay. So we determine this energy density of a magnetic field in a solenoid. Okay. Whose inductance L. This is a previous problem. I'm just going to give this to you. The inductance of this solenoid situation, mu naught n squared times V, or volume. Let me correct myself here. I believe that's voltage. No, no. Yeah, that's volume. Right the first time. Because we did say that inductance deals with the geometry of the object. In this case, the geometry is cylindrical, and so it's going to be area times length of the solenoid, so we get a volume. It's not a voltage. Yeah. Mm-hmm. Magnetic field of a solenoid from a previous chapter. U naught n I, where n is a number density of the wire turns, number of wire turns per length, wire turns per length. N. Substitute L and I, where I is equal to B over mu naught n. One half Li squared. This just becomes mu naught n squared V, because that's L. And the I squared is V squared, mu naught squared, n squared. The n squares go away. We get this one mu naught goes away. And then, of course, we get V squared over 2 mu naught V. So this would be the energy density or just the energy of a solenoid using some substitutions. So still another way of expressing this is the energy of the inductor. Now, just like we, if you recall, energy field density, there is also a magnetic field or magnetic energy density. And since we're dealing with a volume, because we have length and cross-sectional area, the energy density would be the energy per volume. And we have our energy there, V squared V over 2 mu naught V. That just equals, so this will be the energy density of the inductor. So we can use those for sample problems, obviously, all that. Okay, I want to move on, so get the rest. Let's talk about mutual inductance. This involves two or more wires. They have time-varying currents going through each. They induce an EMF in each one simultaneously. So if we have, I'll draw the pictures, two coils, time varying, they have mutual magnetic fields that are set up as a result of that changing electric field, changing magnetic fields. And so they mutually induce EMFs in the other. Mutual inductance. Interaction, mutual induction, interaction of two circuits creating EMFs in either one. It's like simultaneous. So all this harmony, fluctuation back and forth, fluctuates the same rate. Just a beautiful thing. Sit back and ponder it, like this wave-like nature of things, this mutuality, reciprocity. Give over here to this circuit, gives back. And it's like the rate of change is zero. It's like there's no loss. Everything's self-contained. Yeah. Okay. Let's say I have wire 1, coil 1, and I do this because it's coming out towards you and then it's going to wrap into the page. So trying to depict that picture. Well, okay, so the wire's coming out and we have magnetic field line going like this. Okay, let me draw the other one. So it has field going like that, and let's say we have another field. This is all coming from wire 1. And then this field's going like that, and then there's just an example. So there's currents, simultaneous currents, creating simultaneous B fields, and we're going to take the perspective of 1 onto 2, and then we can do 2 on 1, assuming that the time variance is the same. The mutual inductance and EMFs will be the same. Now, it's kind of like basis for a transformer. Now, if you provide more current here, it's going to induce even more inductance here, or EMF here. You can play around with that. But just for the basis, the currents are the same, variance, magnetic fields will be the same, EMFs will be the same, the inductance is the same. So all this similarity, or all of this simultaneous equality, for both. So let's say, look at coil 1. Let's say coil 1 of N1 turns of wire induces an EMF, voltage for current, for electric field, in coil 2 of N2 N2 turns. By a process known as mutual inductance. They are together inducing EMFs. The inductance of wire 1 on 2, which this is proportional to the recipient in turns of wire in 2, the magnetic flux from 1 to 2, divided by the current in wire 1 that produces a flux from 1 to 2. So this would be the mutual inductance of 1 to 2, or it's basically the same. M12 is equal to M21. We're just looking at the perspective of 1 to 2. So, and we can say that because we'll assume for sake of argument that the currents are the same value, or they change at the same rate. Oops, and vice versa. And we'll see. The EMF produced in coil 2 is E2 negative N2, and we know this from Faraday's law. You guys familiar with that? You guys, recall what that is? Faraday's law of induction. Coil 2 experiences this voltage produced by wire 1. It's inducing this state. It's inducing this. And then negative N2 time rate of change of the inductance. Right. Because phi 1, 2, we solve for phi 1, 2. We solve for phi 1, 2. This is going to be M1, 2, I1 over N2. And that's equal to, negative M1, 2 di1 dt. So it's like we're expressing the EMF in terms of the mutual inductance, which comes from Faraday's law of induction, which is dependent on the number of turns of wire. And in this expression of it, it involves both two wires, not just one, or else there'd be just negative N d phi dt. Okay. And from coil 2's perspective, we have the same thing, basically. Negative, or M21 is equal to N1 phi 2 on 1, because now we're looking at 2 inducing an EMF in 1, divided by the current into to produce a magnetic field to provide a flux from wire 2 to wire 1, and the recipient wire is wire 1 with N1 turns. Same. Mutuality. There is no change. There is no one that's greater than the other one, based on the currents being the same rate of change. So that's why we can say M12 is equal to M21. And if current varies with time, which it does, the EMF in wire 1 is going to be negative M21 di2 dt. Because wire 2 has to have a time varying current in order to mutually induce, because it's a pair of them, to induce an EMF in wire 1. That's all this is. Okay. All that is. Since the times are the same, M12 is equal to M21, and thus the inductances, the EMFs are basically the same. So E2 negative M di1 dt, and E2 E1, that is E2, and then E1 is negative M di2 dt, times are the same, M's are the same, and so those are the same. 1 second, please. Okay. So yeah. So E2 is equal to E1, and similar to the EMF produced within an inductor. So it's all this kind of different ways of saying the same thing. We're going to produce an EMF in an inductor. We're producing EMFs between two coils. We can produce an EMF from a changing magnetic field. It's harmonious. A good harmony. Questions? Now, we're going to get into our last section here. We're talking about oscillations in an inductor capacitor circuit. We are going to now look at the relationship of charge to current, charge in the capacitor to current through the inductor. As one is a maximum value, the other one is 0. Maximum charge, no current. Maximum current, no charge, because we don't really have current per se flowing through capacitors. We have charge. And if you have maximum charge, we don't have charges flowing through it, coils of wire. I mean, we do, the time rate of change of those charges, but we don't look at them that way. We look at those charges as current. So one is going to oscillate back and forth. Maximum charge, no current. Maximum current, no charge. We're going to go back and forth, and we're going to see how that oscillation, takes place. Okay. So oscillations in an LC circuit. Now we know from previous chapters that the energy in a capacitor is equal to Q squared max over 2C, twice the capacitance, 2 times the capacitor. And that's just, the energy is maximized when there's a maximum charge in the capacitor. Now, and this is going to be, let's say, at T equals 0. We're going to just have a capacitor fully charged. Then T equals 1 on up, we're going to start seeing that capacitor discharge in the circuit. So the Q is going down, the electric field is going to go down, and then that energy is going to be transferred over to the inductor. It's going to ramp up, Q is going to go down, and then it's going to continue the cycle. We're going to have this back and forth polarity switch and nice stuff. Then we're going to explain this mathematically. So for a circuit as this one here, positive, negative, and let's say that we have open switch there, it's going to close on us. So this is our capacitor, this is our inductor, and that's our switch. We're going to assume our battery's there, but we're just looking at the components of L and C. At T equals 0, there is no current, as I mentioned. We have maximum charge, but no current at T equals 0. When you close the switch, we start getting current. because now the capacitor is going to start to discharge. Got, not current, but charge flow, positive, negative. We start sparking or discharging. At least there's a flow of charge in this electric field. So dq over t dt equals I. At t equals 0, we start to get current due to the capacitor starting to discharge. When that happens, to discharge energy, okay, in the electric field, so we're discharging energy and the electric field decreases. In the electric field, just right, and electric field decreases. Or let me correct myself. That's in electric field, but the energy to discharge energy in the electric field, I just bled stuff together. This should be in. The energy in the electric field decreases. Like that. Okay. The energy in that field decreases. So now the discharge of the capacitor becomes current now in this inductor, because we have now a flow of charge. We got a leakage, or these charges are not held in place, as it were. And now once we get this closed switch, the charges start to flow as current through the inductor. The discharge is through the entire circuit, but notably the inductor. So now when this is switched, is closed, we have current I. So as Q starts to go downward, I starts to increase. We're building up. Circuit. Now some energy is starting to get stored in the inductor's magnetic field after some time t. So we're going to get an energy exchange from the capacitor to the inductor. Once the capacitor is fully discharged, no Q anymore. All of the energy is in the inductor. All right. If I'm moving a little fast, so hopefully you can catch that. All the energy is in the inductor, and now the current approaches a maximum value, because Q now is 0. So taking the circuit, look again. Conventional current this way, what is it flowing to? Negative. And so we have a reverse in polarity. The same process happens. Build up this Q, this dies. We have another discharge, and we have the same operation. It's going to go back and forth, switching polarity. Negative, positive, positive, negative, negative, positive. Current continuing to flow through that inductor. Because, right, this is the flow of positive charges or protons. So once we have a reverse in polarity, we have another discharge starts to happen. And then we have a flow back the other way. So let me correct my direction, flow back the other way. And then this becomes negative again, positive, flow back and forth and back and forth. Get it? Oscillation. Circuit oscillations. This is the key to Tesla. Not the key, but this is what he dealt with. Alternating currents. Except he created a device or some sort of generator or some sort of oscillating voltage source to induce the oscillations in LC circuits, in L circuits, in capacitor circuits, in resistor circuits, or RLC circuits. And we'll see that that produces the most power, and it's all about the flow of the electric field, not the charges, because the charges are not going to flow that fast. It's the electric field, and you get the most oscillations, the most power in alternating current circuits. Beats Edison. Tesla's the winner. Okay. Another discharge happens. Then we get the original state of circuit, which is positive, negative. Because once this discharge happens, it goes the other way. You guys seeing that? You guys tracking that? And then we build up again, and then we come back this way. Or I should do where the original, black. Oh, all right. Let me just undo that. So let's just track. So this would be the second state after the first discharge, and the third state, and so on back and forth. Now, eventually, this oscillation is going to stop. There is, quote, friction in the system. There's resistance. Over time, it take a long time. Put a resistor in there, or even shorter. Nothing is ideally conserved, but we're going to idealize it as if there is no resistance. There is no loss to any circuit device. Oscillation. So this is the concept in an LC circuit. Oh, okay. Green. Questions? You get the concept, the basics. Mass on springs. This is why Tesla made the great declaration. If you want to know, forget how it goes, the state of affairs, the state of the universe, think in terms of energy, oscillations, and frequencies. Because essentially, it indeed comes down to that. It is all that. Look at that mutuality, inductance, back, forth, boom, boom, slosh, slosh, oscillation. Go this way, go back the other way. Keep going, back and forth, back and forth. It's all, this is like the sounding, the bell of nature. Like it's back and forth. This mutual give and take, harmony. So as we know, the energy continues to oscillate forever and ever. Well, no resistance, no loss of heat, no electromagnetic radiation, which we'll be dealing with chapter 34. How do we get a signal from this antenna to another? Well, electromagnetic radiation. How do we set that up? Oscillations. And then we have this big wave going out at a particular frequency. We can chop it up. We can take that frequency and we can do something called a Fourier series, or Fourier series, and look at the different frequencies of that by which that one frequency is made of, and we can get different radio stations. It's all energy, waves, vibrations, frequencies, all that. I'm glad I can appreciate that statement today. Okay, so consider an arbitrary time t where Q hasn't quite reached its max and I hasn't quite reached its max. So energy is stored in both the capacitor and the inductor. The total energy of that circuit will be the sum of the energy in the capacitor and the inductor, which is Q squared over 2C plus, we just derived this, 1/2 Li squared. And okay, so let's assume that this is a self-contained circuit. Oh, all in air, closed system off from environment, conservation of energy, just changing forms. Changing forms. Potential kinetic, not really, but you get the idea. Potential kinetic equals total. Total energy of a circuit is the energy in the capacitor and the energy in an inductor, and these are the terms. Don't tell me that there's no harmony. In a conservation environment, the resistance is equal to 0, and there is no electromagnetic radiation. All right. Then the rate of change of energy, we just talked about that, power. The rate of change of both sums, Q squared over 2C plus 1/2 Li squared. And when we do that, we are going to get Q divided by C, dQ dt. Because dQ dt is current, and so we can take the rate of change of Q. And this will be the result. Q over C dQ dt plus Li di dt. And sum of those changes equals 0. Now, if we wanted to solve the charge as a function of time through this capacitor, we'd have to manipulate this differential equation in a nice way to get started, because right now the differential equation is in 2 variables, so we have to, get into one. And one way we can do that is but before I do that, you guys see what I did here? Make sure you understand this. Taking derivative with respect to Q, that's current. So this is 2 over 2 QC. Those 2's go away. Q over C, dQ dt. Right? And then we have time rate of change of the current. 2, take this down, it's going to be 1 Li di dt.
Yeah, I get it.
Yeah. So it's like a chain rule. So we just, taking a derivative, that inner function, and then we just, have an expression for the Q. For the Q and for the I. As a whole function. So as a whole function. So it's just a chain rule. So that's what we have. Now we have two variables. Well, we know that dq dt is current and di dt is, we take the derivative again, so that's why we got d squared q over dt squared. If I is dq dt, then rate of change of this is the second derivative. Right? So now we have basically one variable. So this becomes q over c I plus li. Well, we're getting there to one variable. D squared q over dt squared equals 0. I'm just going to do all the middlemen. I'm going to do explicitly. This is, we bring it over here. Li d squared q over dt squared. Those i's go away, so now okay, bring it back. Q over c plus L d squared q over dt squared equals 0. Now this is a second order differential equation. We've been dealing with first order. So follow me here. So I want to get q, so I'm going to take the expression with all the mess, the junk, have it on one side, because I'm going to eventually get a natural log, but I got to, do something. D squared q over dt squared. And, the other stuff goes on the other side. That's going to be negative 1 over LC times Q. So it's not, we can't just, we got to do some substitution. So I like to call this the quadratic method of solving a second order differential equation. So we can make a substitution variable, call it r squared for this entire thing. And then that's going to be negative 1 over LC times Q. And I'm just going to say, going back to mass on spring systems, this 1 over LC business is going to be equal to, angular frequency squared, negative omega squared, times Q. Well, I was going to put X because, when we do a mass spring system, we're talking about acceleration equals stuff. And so it's a similar fashion. And this angular frequency omega is going to be equal to the square root of L over 1 over LC. Sorry. So therefore, omega squared is 1 over LC. So it's this. That's where it all comes from. Substitution. All right. I will leave that up and go to next. All right. Okay. All right. So we don't want d squared, we want just dq dt. So we'll take the square root of that and take the square root of both sides. It'll be r equals the square root of negative omega squared q. And this just becomes plus minus, because there's instead of plus minus I omega q. So we're taking the square root of that simple or direct reason why we don't take the square root of q. We're taking the square root of those substitution variables. You know, it's basically the reason for that. So we leave q outside of everything. Substitution variables are r and omega. Right? Or omega is square root of 1 over LC. So if r squared is d squared q over dt squared, then r is dq dt. So n plus minus 1 over square root of LC, you know, same, times q. So now we can solve it in our normal way. We just had to do, you know, we had to break it down, we had to break it down to get to the simpler form. This first order, you guys can do that. We started to see you can get that stuff okay. So let's get the q's on one side, dq over q. And this is plus minus dt over the square root of L over C. And you know where this is going, right? So we're going to take an integral from q naught to q, where, you know, because we started, you know, it's not at a maximum q, so we're going to rise up to a max q. We can call this, you know, max if we want to, dq over q, and then that's going to be plus minus integral dt square root of L over C. This comes out of the integrand. And then we have natural log of q max over q naught. So let me see. Because when we discharge this capacitor, we're actually going to have this q naught over q max. So we're going to change the order. Of our integrands. And so q naught, q max. And I did that because remember the natural log rule, natural log of q naught minus natural log of q max is this. All right, so then that becomes plus minus t over square root of LC. Then divide both sides by natural log, we're going to get q naught over q max, or just q, you know. It's going to be E plus minus T over square root of L over C. And Q, as a function of time, is equal to Q max. And this expression here, you know, it's just a math identity, if you will. And Q max cosine omega T, because remember, omega was 1 over the square root of L over C. Omega times time. Plus a phase shift. Like if we weren't starting at the regular cosine function at the maximum amplitude, we shifted it over. That's your phase shift. So we're going to put that in there as a general. case. So you can just see by the equation, you can just see by the math that this is a wave. It's oscillation back and forth, cosine function. Q of t, Q max, cosine omega t plus phi. So this is the charge in a capacitor as a function of time. You know, at t equals 0. I mean, because we're keeping with the nomenclature, the concept that at t equals 0, we have Q max, and then we rise up to some, it discharges to some Q. And then the current is gonna, you know, be flowing. We term omega 1 over square root of L over C as the angular frequency of the circuit. So this circuit is oscillating from charge to current and back and forth, reversing polarity. So it's not swinging back and forth. The current and the charge or have a harmonious ebb and flow. Harmonious ebb and flow. Questions? So this is the angular frequency of the LC circuit. Now the current is going to be the time rate of change of the charge, dq dt. Now again, a chain rule operation on this function. You know, the derivative of cosine is negative sine. So we're going to do chain rule. We're taking omega out. And it's negative omega q max. All right. Negative omega q max sine omega t plus phi. And let's find this phase factor, phase shift deal. Okay, at t equals 0, again, current is equal to 0 through the inductor, and there is maximum Q. So that's why I have to change my limits from Q max to Q. So going back to the, this equation here. So no current equals negative omega Q max sine phi, t equals 0. So then we know that there is no phase shift, phi is equal to 0. So we start at the natural sine and cosine functions. There's no shift. That's what this means. So Q is going to oscillate in the normal cosine way, and current I will be negative sine way. You know, where this is your max current, charge flows up, right? Because the charge is the orientation, if you will, perspective. You know, we're going to have a buildup of charge from the opposite, you know, direction. So negative Q max and negative I max, because we're shifting. When this goes to negative, that means that the current is going the opposite direction, back, forth. When the current is maximum in this direction, we have basically 0. So it's not to scale, but you know, we have that. And there is your mathematical, graphical pictures of the oscillations between the charge in a capacitor and an LC circuit and the current through the inductor. So when one is min, the other is max. Boom, 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 bam. And we can see that harmony between sines and cosines. You know, when sine is maximum, cosine is min, and they're off by a phase shift of pi over 2, which pretty much dictates why one is going to be a max at some number, and the other one's going to be a min or 0. So consistent. So again, more on the phase shift. Phi equals 0 is consistent for Q equals Q max cosine omega t plus phi, because as this is 0, we have the maximum Q at t equals 0, because this cosine of 0 is just 1. So Q equals Q max makes most sense, right? T equals 0, Q max. Before the discharge degrade, this goes down. Oh, I'm increasing. Okay. I'm setting up maximum current. So in the so-called opposite direction. The so-called opposite direction, because remember, we had our orientation positive, negative, and so we went this way because it's going to be a discharge through the electric field. And so current is going to be in the so-called negative direction. So Q equals Q max. We got a little bit more to go, and we'll be done here. At t equals 0, before the discharge degrade. All right, and so then Q equals Q max cosine omega t. This is general, and then current will be the derivative, which is negative omega Q max sine omega t, which is basically equal to negative I max sine omega t. Just that. Whoops. Now, let's go back to the energy in this entire circuit. We've abandoned that. Energy in an LC circuit. We know that total energy is the sum of the energies in the capacitor and the inductor over 2C plus 1/2 Li squared. Well, now we know that there's a wave-like or time dependence here. So I forgot to write all that in, because we're just taking the values of Q max, without the phase shift, and attaching the cosines and sines. So we'll have Q squared max 2C cosine squared omega t. Why? Because Q max cosine and square plus 1/2 Li squared was I max is going to be squared. Now it's just going to be sine squared omega t. Cosine squared plus sine squared is 1. So Q squared plus that is equal to total. Now, let me add another bit before we get there. Now, fluctuations, oscillations between energy stored in between energy stored in a capacitor and an inductor. Okay, there's going to be a fluctuations. So when Q squared over 2C is max, 1/2 Li squared is 0. And vice versa. And lastly, since that is the case, when one is max, the other is min, and this is max, the other is min, the energy values or the amplitude on a graph would be the same. When one has achieved the max energy, the other one is 0, because the total energy is a sum of these. If this is all max, this doesn't exist, and so all the energy is encapsulated. All the energy is held here. That makes sense? So the energy amplitudes are going to be the same for either component, for either one. For the capacitor's max, this inductor is 0, and the inductor's max, the capacitor is 0. It's going to be the same for either when either is 0. So we have a situation Q squared max over 2C equals to Li squared max over 2. And we get this from knowing that cosine squared plus sine omega squared is 1. And since I is negative, yes, but when you square it's positive, and so you set these guys equal. So this was Q squared max over 2C plus this equals 0. Set it equal. They're equal. So the total energy Q squared max, the total energy in an LC circuit, cosine squared omega t plus sine squared omega t is equal to Q squared max over 2C, which should make total sense because this is when T is equal to 0. All the energy is in the capacitor. All the energy is in the capacitor. It all comes back. Beautiful thing. When T equals 0, we have this right here. That was our first picture. And so it is 4:31. I didn't want to rush. And so we'll continue tomorrow we'll go to chapter 33. And we could look at the RLC circuit. I'll figure that out. But chapter 33 tomorrow, and chapter 34 on Monday. How are you guys? Sounds good?
Yeah.
All right.
Yeah, it's over there.
All right. Any last questions on any bits as we close up? Any part of this derivation strange? Okay.